Hi there. In this lecture, we will be discussing the concept of curse of dimensionality, which affects a number of machine learning classifiers. So, we will discuss curse of dimensionality in different contexts for different machine learning models. So, the first one we discuss is the k-means, the k-nearest neighbors classifier, which basically says, okay, you take a test example and you classify it with a majority vote. You take the k closest training examples to the test example, and you take a majority vote of the class that every training example from among the k examples belongs to, right? And that's basically how a k nearest neighbor model works. So let's see what's the problem with this model when we increase the dimensions. And actually your dimensions correspond to the number of features. So if you have a single dimension, you would, for example, you could have this kind of data, and f1 is the first feature, and then when you add a second dimension, it could look like this, and when you add a third dimension, it could look like this, right? So it's obvious that the sparsity decreases when you increase the dimensions. So a natural consequence of this, the average distance between two examples increases as we increase the number of dimensions. So given that you have just a fixed number of training examples, then you could, if you keep on indefinitely increasing the number of features, you could end up with a very sparse, distribution of the data, right? So now what happens if you take the k closest neighbors? If you take the k closest neighbors, you could end up getting training examples that are not exactly close to the test example, right? They could be kind of far away. So that now raises grave questions as to whether the training examples, the k nearest neighbors, could be used for categorizing the test example, because they need not be close to the test example, given the number of dimensions and the sparsity of the data, and the fact that the average distance between examples increases when you increase the dimensions. So, and what would be the kind of magnitude of data you would need if you increase the dimensions in this manner, right? So supposing you need 10 examples here, then ideally you would need 10 squared examples here when you take two features, and you would need 10 cubed examples here. In order to get the same density, right, if you take 10 examples here, you would need 10 squared examples here, and you would need 10 cubed examples here, right? So that means that the data has to be exponential in the number of features, right? If you have d examples, you need 10 to the d examples, which means the data would be exponential in the number of features in order for this model to work effectively. And the similar issue happens with k-means clustering, because you could end up getting clusters that in which the examples are far away, right? But they've just been clustered because they are close to each other than the rest of the examples, right? So again, you could pose grave questions as to whether really these examples need to be in the same cluster or not. The next model we discuss is the Bayes classifier. So the Bayes classifier could be used for continuous as well as discrete data. So normally the approach is, if you have continuous data, then you could model it using a parametric model, which basically says, okay, that you find out the means of each feature of each dimension. You find out the means and covariances, means and variances along each dimension, as well as the covariances between the features, right? So when you do that, you end up getting d into d plus 1 by 2 covariances. This figure here combines the number of variances and covariances. And in addition to this, you would also need d number of features for the means. Okay, so you would need d number of features for the means along different directions, right? So you need approximately order of n squared number of parameters to be estimated. And the rule of thumb is, for example, for every parameter to be estimated, you need 10 examples. So it would be 10 into this figure. That's the amount of data that you would need. Okay. Now different people would have different conventions, but okay, let's just say it's a constant times the number of features, right? And you could have, for example, 10 examples. So then you would need 10 times this 10 times this value. That amount of data you would need. And so in this case, the amount of data you would need is big O of d squared, in the number of you need big O of d squared amount of data. And for the case of discrete features, again a Bayes classifier, basically you are finding out the posterior probability of C under x1, x2, and so on up till xd, and that using Bayes rule would be probability of x1, x2 up till xd under C, right? And this needs to be estimated, and you say that you see that this this is a joint probability, right? So the problem lies in estimating joint probabilities. For example, let's say you have a single feature and you need 10 examples to estimate the probability distribution of this single feature, for example. Then in the case of 2 dimensions, you would need, for every value of x1, you need to estimate the probability distribution at x1, right? And that would be similar to the single dimensional case, right? And you need to do this in order to estimate the probability at all the points in the plane, right? So which means that you would need 10 examples for each value of x1, okay? Which means that if you need 10 examples here, you would need 10 squared examples here, okay? So, and if you have d number of features, then you would need the 10 to the d number of examples. So again, you see that in this case, the amount of data you would need is exponential in d. Now the last case we consider for the effect of curse of dimensionality is in the case of discriminative models. Now let's just take an example, and the circles represent one class and the x's represent another class. So you see we have some outliers here for the circles. There's one outlier lying here, and we have an outlier for the x's as well, that one here. But still we can draw a linear plane of separation, okay? But the problem with this linear plane of separation is that when you have more realistic examples of both the classes, for example, the examples marked in red, right? So you have one red example here, the one, for example, a test example here, which is a circle, and you have 2 test examples here which are crosses, and these are realistic, they are close to the original training set, right? But these examples would be classified incorrectly by your classifier, okay? Because this classifier is actually doing overfitting and is trying to accommodate even the outliers, and which leads to incorrect classification of more realistic examples. So, what is how is this? What has this got to do with course of dimensionality? It turns out that when you increase the number of dimensions, it's more easy to find a linear plane of separation, right? Because as you know, typically when you increase the dimensions, the data is sparsely distributed. So chances are more that you would get a linear hyperplane of separation. But that linear hyperplane of separation, which would separate out the examples 100%, would be an example of overfitting because it may not classify more realistic test examples. So, what's the solution to this problem of overfitting? The solution would be that you do regularization. And for example, in the case of SVM, you choose a line that has a safe margin on both the sides, right? And that's what regularization would do. Okay, so regularization could be done in logistic regression, SVM, and neural networks as well. Okay, so this is a bit about the curves of dimensionality and what effect it has on different machine learning models. And thank you very much for watching.